All right, next on our list is to look at evaluating limits numerically. We looked at limits graphically, we want to look at limits numerically, and we'll also look at limits algebraically. So sometimes this is a very boring question, and this is where people can get mixed up about what is happening to the function right at x equals 5 versus very close to x equals 5. So this question is absolutely asking what happens when x is close to but not equal to 5. The deal is that this function, 2x squared plus 1, this is a parabola, it's continuous. So whatever the y value at x equals 5 is, when you're very close by x equals 5, your y values will be very close to that. So there is a link between limits and continuity, and we'll formalize that in a minute, but for now we're just focusing on the limit part mostly. So here, if you plug in 5, we get 2 times 25 plus 1, or 51. And it is absolutely true that if this graph goes through 5, 51, then any x near 5 will give you a y near 51. The good news for you is that when you're finding limits numerically, well, really any way you're finding limits, it should be very obvious when you hit an interesting point where there's a discontinuity. So the next example is great for this. We are now looking at what happens to the fraction e to the h minus 1 all divided by h if h is really close to 0. So we can try plugging 0 in, and we get 0 over 0. And that is, I hope, clearly undefined. We cannot have 0 in the denominator. There is an interesting thing that we'll come back to at the very end of the quarter, but it's also important now. If there was a 0 in the denominator but not the numerator, that's asymptotic behavior. That is some sort of vertical asymptote, and your limit is either going to be infinite or not exist at all. When you get a 0 over 0, that's this really cool exception. Graphically, that's when you get a hole in the graph, otherwise known as a removable discontinuity. Removable because it's just one tiny little hole in the graph, so if you just fill it in with a single point, you've removed the discontinuity. If you have an asymptote, I don't care where you put a point, it's not removing an asymptote. It's still discontinuous. So when you hit these, we will work on these algebraically as well, but this is a great example. I don't have an algebra trick that would fix this anyways. So if all else fails, we can always go back to evaluating these numerically. Evaluating numerically, just like when we were trying to find slopes of tangent lines and instantaneous rates of change, means choosing points really close to what you're interested in. So if I want points really, really close to 0, I want to try, for example, maybe negative 0.1. And then we want to build up a little bit of a pattern so we can make sure we don't catch a fluke. We're going to pick another point that's even a little bit closer, and another point that's even a little bit closer. So this is not the only way you could set up this table. You could use negative 0.2, you could start with negative 1 and then do negative 0.1 and whatever along those lines, but build a pattern where you're plugging in numbers very close to the number you're interested in, and always build the pattern up on both sides. It doesn't actually have to match perfectly, but it's pretty easy usually to just make them match perfectly on both sides. So we'll just plug in the positive and negative versions of that. This is basically just going to be a little technology problem. Find your favorite graphing calculator and plug this in. If you're using Desmos, you can get it to save you the work of typing this in over and over again. So let's check it out. And you can choose how to do this. You don't have to do it the way I'm about to. I just like to show you different tricks as we're working here. I think I'm actually going to build the table. So I'm just going to give this a function name so that it'll plug things in for me. I'm going to call it f of h, and we want that to equal e to the h minus 1 all over h. So we've got a graph. We don't really need it, but I like that I can build the table in here, although you can use the graph to check yourself very nicely. So what I'm going to do is tell it to put f of x1s in here. So that means I type what I want for x1, it will put f of x1 over here. So it's important that you do function notation up there so that you can refer back to that function. And I wanted to see what happened when I plugged in negative 0.1, negative 0.01, and negative 0.001. And you can even put that 0 in the middle to see your undefined, which we already checked. And then I want to build up my other side as well. So 0.001, 0.01, and 0.1. And again, the trick with these is always to try and build your table so that as you move in on your table towards the 0, your x values actually are getting closer to the 0 as well. And then we can look and we can say, okay, my y values, they were 0.95, 0.995, 0.9995. They look like they're getting really close to 1 as I get close to 0, but we always have to check both sides. So on the other side, I started at 1.05. I got closer with 1.005, even closer with 1.0005. So I would say, yes, my y values are approaching 1 on both sides. Since we are in here, we can check ourselves graphically, but I need you to be able to show me that algebraic work. So you can see there, and it even plotted the points for us, that we don't seem to have anything too weird going on. Our y values really are just getting close to 1. Notice that Desmos doesn't show you that there's an open circle there, that there's a removable discontinuity, so that's something we have to be able to figure out on our own. Okay, so that does it, and I would just copy the numerical values down in your table. Maybe give yourself like 4 decimal places so you can see that progression. And I think that's great for showing your work, just showing me what those values were so that I know what you were looking at. I'm going to be lazy and not do it, but I have one more in here, so you can pause and try this one on your own and then come back in and double check if you would like. I'm just going to do the same thing. I'm going to go plug this new formula into Desmos and explore what's going on. So up here, I'll change this to 5 sine 2 pi. To get the pi, you can just type pi, y minus pi. And then in the denominator, I have e to the y minus 1. Oh, and it's not going to like that. Hold on. Use a parenthesis. Minus 1. There we go. Minus 1. And I've made it unhappy. One thing is that I've changed my variable to y. And that fixed it. Excellent. So this is great, but I can't use this table because I was asked to find the limit as y approaches 1. So I'm absolutely going to have to be a little bit thoughtful here. The limit as y approaches 1, I want values just smaller and just bigger than 1. So I could try something like 1.1, 1.01, 1.001. Fantastic, very similar to before. Be careful, you all know this, but it's really easy to brain fart here. On this side, we don't want to plug in negatives. We want to plug in 0.999, 0.99, 0.9, something along those lines. So that's how I will build my table in Desmos. So I'm just going to go through and edit 0.9, 0.99, 0.999, and then on the other side, I can just make those ones. 1. And there's a really nice, quick, easy way to build yourself a table. If you have to make one in class for a mastery test, you will have to do it on a calculator, but for your homework purposes, this maybe will save you a little bit of time. So now I'm looking on the left side as my x's get really close to 0, my y's get really, really close to, I don't know, 31 something. On the other side, same idea. My y's are getting really close to like 31.4-ish. So I would say negative 31.4, that's a decent estimate of what you're getting. Or if you want to do a little bit better, maybe take these two and average them. So take the negative 31.43143 and average it with the negative 31.400015. But I'm not expecting you to get crazy close. I'll tell you if all of a sudden I want you to try and get within, I don't know, 3 decimal places, but 1 or 2 is probably good for my purposes. So back here, if you're doing this for a test, please write down what you were looking at so that I can see what you were making your decisions based on. But I would say something like negative 31.4 is what we're getting. Interesting, I saw that that one gave me, oh, you know why? I think I know. I was going to say, why is it giving me 0 instead of undefined? I'm pretty sure it should be undefined, but it's because I didn't put the 1 in the middle. I fixed everything else on the table. So it is undefined. And if you check that by hand, you should see that you're getting a 0 over 0 again. So remember that 0 over 0. That's called an indeterminate form. Those are fascinating because anything can happen. It could be undefined, it could be infinite, it could be 0, it could be 1, it could be anything at all. So these we really like to check out. They have possible removable discontinuities. Okay, so that's finding limits numerically.